Hello, everyone. My name is Tom from Serendipity AI in London. And today I'm going to talk to you about spotted signals in text via natural language understanding. So this is the state of the world of data today. We have an exponential growth of data that is being created, captured, and copied worldwide. We started with just a few gigabytes of data just a few decades ago, and the projection for the next years are going to reach an enormous amount. We are talking about billions of terabytes. But what's the difference between information and knowledge? Information is just what we would call some spread data points that might be tagged, might be different from one another because of their intrinsic properties. But knowledge is what we call having a structure between these data points. And as John Naisbitt said, we are drowning in information, but starved of knowledge. Our approach to dealing with this amount of information and that is being released every day, we have a twofold steps. So we apply AI at first to identify the signals between this vast amount of data and to basically distinguish the signals from the noise. And then with the second step, we want to extract also the knowledge from the signals themselves. And we will delve into this twofold approach in the next few slides. So why signals? So signals offer potential for strategic advantage in a multitude of domains, from artificial intelligence to climate change, finance, or economies. And they can be used also in downstream tasks that we will see next as information that can be then analyzed and converted into knowledge and into wisdom to offer a strategic advantage to end users. So what is a signal? Signal are the emergent pieces of information relevant to a given context. here we have an example of an article talking about EU markets. And as we can see, this is an excerpt of the article. We identify these as our signal. Major economic indicators show that Europe is caught in a protracted corporate and technology crisis. This means that this particular part of the article is interesting to us, relevant to a given context. The detection of this excerpt is based on next word prediction, which is the basis also of current language models, which were trained previously on very large corpora. The text itself is a pre-processed, segmented first. So this means that each single sentence is identified and cleaned from irrelevant information that we don't want or we don't need to process. In this case, we have a collection of potential signals, and that each of them has a type, and here we have a collection of different types. The goal here is to understand whether a specific excerpt of the text is somehow linked to any of the types through a relationship that is then discovered via next word prediction. So the prompt here that is submitted to the language model is literally this text is about and the corresponding signal type. And in this specific example, we can see that for a confidence that is equals to 0.99, we have identified this particular signal as of type crisis event. There are several differences between classic methods for signal detection and methods that are based on language models. So first of all, classic methods are type dependent because this means that we have to create a model specifically to extract a given signal type. So for the example earlier, we would need to, first of all, label, collect the data to be labeled as a crisis event or not. So basically a binary classifier, and then annotate it manually to then achieve create a benchmark, create a data set that can be used to train the model. Instead, the language model is type agnostic. So this means that regardless of the signal type that we want to extract, we can use these language models just by querying them using prompts. The classic methods also are need or tedious data annotation, whereas language models use a zero-shot approach where there is no need to pre-train the model in order to query it. Classic methods also use supervised learning, whereas we have self-supervised learning, which is which don't also depend on training data or fine-tuning data. Typically, classic methods also exploit algorithms that cannot or can hardly be used on GPU hardware. And therefore, also we have a difference in the performances in terms of the runtime that is needed to execute them. Then we get to the second step, where this first step was signal detection, and now we want to extract the knowledge from the signal. And the questions that we are going to answer are which actors are involved. So given a signals, what kind of actors, so the entities that are involved in the signal itself. What is the subject of the signal? Which categories also does it belong to? And what is the signal strength? And the signal strength is different from the confidence because it says how impactful the signal is. Whereas the confidence only says that that a given signal has a probability of belonging to a certain type. One of the most used methods to extract actors from text, or in this case from signals, is named entity recognition. And in this particular example, we have two entities that are visible, economic indicators and Europe. And both entities can be linked to a knowledge graph. And in this case, we are taking it as example, the Wikipedia knowledge base, where economic indicator and Europe are two entities in Wikipedia or Wikidata, if we are considering a structured knowledge graph. Then let me introduce another example. And the example is another signal, signal type hazard. And that says with the aging of the population, the prevalence and incidence of stroke in China are increasing every year. And here we have, again, two entities, and in this case, stroke and China, that are linked to our signal. Named entity recognition is a powerful tool, but it has limitations. It only says that a signal talks about a given entity, but it doesn't say in what context the actors are mentioned. So what are their roles with respect to the signal? Is it any relationship positive or negative? And here we employ large language models to that have been trained on Wikipedia data as well, and they learn an intrinsic map between text and entities. So the actual prompt that we'll submit to the language model is, given the text above, return the target of the signal as a Wikipedia URL. So what the language model will actually perform is the extraction of the actual entity that the signal refers to. And in this case, beyond the extraction of stroke and China as two separate entities, we can finally find the target of this signal as the demographics of China, which is much more relevant to the signal itself. And this is being done even though demographics of China as an entity itself is never mentioned explicitly in the signal itself. So signal understanding is what we call as the linking of the signal as an entity to each entity in the knowledge graph that we deem somehow related. to the signal itself. We already linked the type. We already found the target and the strength. The strength is also detected, is also inferred using a prompt that can be that can extract basically extract medium as one of the potential targets. Also, we have the assessment of the impact of the signal. So what we actually ask the language model is how impactful is this hazard, and as options for the answer we have low, medium, and high. And in this case, we extract a high impact. Then how many people are impacted? Large language models also have an intrinsic knowledge of what it means to be to have a in this case a health hazard in a region with as many people as China. And in this case, we have a 10 to the power of 8 people, and extracted from the text hundreds of millions. And also we can link the signal itself with the categories from our internal taxonomy, and so link the signal to members of the taxonomy. And in this case, we are talking about the China as a country and the healthcare. And here we have the potential downstream tasks. The first one that we introduce is the signal clustering. And here we have an example of a map where we have international relations, energy, foreign policy, economics. So each signal belongs to a given cluster. And the cluster themselves that we can find here as the circles are again clustered and displayed closer to other clusters that are related in meaning. And we're doing this via neural topic modeling. And we label the cluster automatically, still using generative AI, and classify by the clusters by our internal taxonomy of categories. What happens when we introduce time into the equation? We can also plot the volume in function of time, and we can perform time series forecasting for the following months. And here we have a couple of examples. In this case, we have African politics and Israel-Palestine relations. And in this chart, we have the volume, in this case, the y-axis. The color is the sentiment. So green means positive signals, and red means negative signals. We can also apply stem series forecasting, and in this case, from just after May 2022 to June 2022, we can forecast the volume and the sentiment of the next signals that we find in our corpus. And then event detection as well, with the own titles assigned by generative AI. We can also understand the causality, so what links the signal to the scenario. in this case, starting from a single cluster about climate change, using still generative AI, we can ask the language model to analyze the state of the art of the world, and to predict possible futures, so possible scenarios concerning a certain context. So in this case, a major oil companies announces plans to transition to clean energy by 2050, and so on and so forth. And all these possible futures can be extracted solely through generative AI applied to a corpus of data that is curated and analyzed, and where signals are extracted from it. So the conclusion: we spot signals via NLU, which is based on a two-step signal detection and signal understanding. Why we do this? To enable strategic advantage from knowledge, and perform efficient and automated access to tailored insights. Our two publications here, one in LSE, London School of Economics, and Forbes, you can access through, if you get to the link to the Zenodo presentation. The current and future work, we are currently working on scenario and implication. And this is the 5-step pipeline that we are currently following. The future work about the last step action involves advanced personalized recommendation using the data that we collected. So thank you very much. Yes.
So it seems to me that kind of your approach here is more or less, you're kind of codifying the knowledge that is. Do you want me to speak into a microphone, or?
Is it working? Sorry.
Sure. Thank you. So it kind of seems to me that with the approach that you're using, you're kind of codifying the knowledge that exists within the existing weights of the large language model. Given that you're using kind of zero-shot, self-supervised approaches, how do you know if you're right?
Right. Yes. The fact is, there is a substantial difference between analyzing a specific example and analyzing something like that can get a bigger picture. So language models are great, not for the former, but for the latter. So in terms of analyzing the analysis of the single context, maybe we should not trust them in terms of the atomic piece of knowledge. But for on the other hand, in order to analyze a higher and a larger amount of data, we are going to exploit the capabilities of machine learning models in finding patterns, and that's what we are interested in.
Thank you.
There are also ceiling mics, so you'll be picked up if you just speak up a little bit.
Okay, that works too. Or I already got it. You mentioned, and I have to look at my notes, an internal taxonomy of categories that the signals are mapped to. Was that taxonomy created by humans or generative AI? And also, or was it borrowed from Wikipedia, which also has a structure?
I couldn't hear you well.
Oh.
So,
Okay, I
I'm
don't know
sorry.
what's going on. Can you?
Is it on?
I don't know. I'm sorry.
Okay.
How can I be more awkward? Hello. You mentioned the signals being mapped to an internal taxonomy of categories. I'm curious whether that taxonomy was developed by humans, or was the taxonomy developed by generative AI, or was it borrowed from Wikipedia?
Yes. So the taxonomy was developed internally by an extensive manual mapping
Oh, great.
of the using a top-down approach. So so basically, after analyzing a huge amount of data with experts, coming from different fields, and interacting with them, and so the final taxonomy was the product of a long-term brainstorming that actually never ends, just because these, especially these taxonomies are based on the state of the world that is dynamic and is constantly changing.
Thank you. Can you go into a little more detail on how you trained the language model on the Wikidata? Like, was it like a self-supervised process, and were you like trying to predict like connected nodes, I guess, to that kind of stuff?
Yeah. Are you interested in which models in particular, or is it a more generic question?
Yeah, I guess both. If you have like a specific model name, I guess.
Yes.
The process.
The process itself. Yes. Yes. So the different models that we employed in the two phases. We start with the signal detection, and the signal detection is performed by with a model that is from the BART family. BART models normally expect a prompt to be evaluated, and the prompt is basically the somehow says the type of instruction that we want to the type of information that we want to extract from it, and in particular for the signal detection is the extraction of a topic, and the topic itself is defined as a signal type. And the second step, the signal understanding, is performed using several models that go from generative AI. Using also GPT, generative pre-trained transformers, and together with other uses of the BART model itself.
Okay, thank you.
Thanks again, everyone.